So welcome everyone to the Inspiring Math Minds, a virtual learning series hosted by the California Math Council Central Section. But really, we're taking over the whole CMC statewide stuff now, Pam. They just haven't figured that out yet, but we're working on it. And in addition to the California Math Council, we want to thank all of our county office partners in the Central Section that have joined with us to help us promote our events and help us find amazing speakers like the one that we have here today to help us build our community and our knowledge in our area for our students. In addition, we'd like to thank the Gates Foundation, who's also helping sponsor and support some of the work that we're doing around high quality instructional materials as our state gets ready for the upcoming adoption. And so with that, I'm not going to delay us any longer, and I'd like to introduce and welcome to the stage Pam Harris. Pam, go ahead and take it away.
Thank you very much. I caught the ball and I tried again. Dribble, step, step, shoot. Coach said, nope. Caught the ball. I tried again. Y'all, as I was learning to play basketball, I just could not figure out how to do a layup. You know, that's that cool thing where you're thing. I was excited about basketball, but there were some things that just couldn't make physical sense to me. While I was learning, my coaches allowed me to play the real game of basketball. They let me on the court. I could dribble, shoot. I was pretty good at defense. As I was learning to play, they let me play the real game with what I could do. The system was set up to put me in games and let me have fun while learning. Here's what they didn't do. They didn't say, for some reason, you're not naturally picking up on a layup, so we're going to put you over here, and you can just play this other game. It's like a fake game. Just memorize these rules and then mimic them since you can't naturally get it. You're just stuck playing this fake game. As we think about current math education, is it possible that the system has been taking students who don't naturally pick up on math and relegating them to a game of fake math, where students are asked to rote memorize rules and mimic procedures? What is the real game of math? Is it rote memorizing rules and mimicking procedures? Or is it something else entirely? What if the real game of math is letting students play with what they can do, with what they do know? When students can't just figure it out, could we find out what they can do and then use that to help them learn the next thing? Just like me, every person on this webinar tonight is excited about teaching and wants to reach more students. It might have taken me longer to do a layup. I needed more experiences than many people. Y'all, I remember the day my coach screamed, "Pam, just did a layup." It was a little embarrassing. I know that you want your students to have the experiences to learn the real game of math. That's why you're here today. When we understand the real game and how to teach it, we can make that happen. I'm Pam Harris, and I believe that math is figure-outable, and we can teach it that way. My basketball career actually didn't end with that layup. I went on to play internationally. But more importantly, for the past 20 years, I've been playing real math internationally, helping teachers and leaders just like you get more success and have the confidence to reach all of your students. Tonight, I invite you to do 3 things with me. So 3 things tonight. First, what do I mean by using what you know to play the real game? What is the real game of math? So the first thing, how do mathy people actually math? Second thing, to see the shark. And then third, to avoid traps. So let's do those 3 things tonight. Before we dive into that first, I'm going to invite you in the chat. What are you thinking about when you hear me talk about playing the real game of basketball and the fake game of basketball or math? What is the real game of math to you or the fake game of math? What do you think of my true layup story? So just put a couple of words in the chat. Let's kind of see what you guys are thinking about. And while you do that, I'm going to share my screen. Hey, Annie Fetter. Yeah, thinking versus rote memorizing. What does it look like to rote memorize basketball? What does it look like to rote memorize math? False starts. Sure enough. Now, what does procedural fluency mean? I kind of like to talk about that a little bit tonight. I find the term procedural fluency tricky. And I know that it's in the standards, and I know that it's in, oh golly, it's the NCTM. I'll come up with it. Well, it was in summing up, but it's also in, what's the NCSM NCTM teacher, where it has the 8 essential teaching practices.
Principles to actions.
Thank you, principles to action. So I know it's in there. Well done, Duane. Well done. I know it's in there. Yeah. What is the place of procedures in mathematics and mathematics teaching? And let's raise those questions tonight. All right. Thanks everybody for some feedback on that. Let me just read a couple more. Ridiculous. Kids don't ever get to play the game of basketball. Also basketball player. Nice. But often they don't get to play the real game. Yeah. Like what is that? Do we really ever just take kids out of the real game and say, it's not working. Like play this fake game. Is it possible that many of us were raised in the fake game and don't even know what the real game is? Pick me. Like I was an adult before I began to realize mathy people do different mental actions than I was doing. And it was actually quite disconcerting, and maybe we'll call it a little bit of a midlife crisis, where I had to come to grips with the fact that I was a high school math teacher, and I was realizing that the things I did, the mental actions I did, were not the same mental actions that mathy people I was interacting with. Now, careful. I just had a nice, lovely chat with Joe Bowler the other day. She was on my challenge as a special guest. It was brilliant. And she pushed back a little bit and she goes, Pam, there's no math gene. And I said, I'm not saying there's a math gene. So to be really clear, I'm not saying that you either have it or you don't. What I'm saying is that it took me a while to figure out how to do a layup. But while I was figuring that out, I got to play the real game of basketball. What is the real game of math? And I think there are people who, let's be just clear. Michael Jordan, there I'm aging myself a little bit. Kobe Bryant, there's a little bit newer. I was gonna have a more current basketball player. Now I'm not coming up with that one. What's her name? She's so good. Anyway, that one. Caitlin. Like Caitlin Clark. Like if we look at, come on, y'all, they have some natural talent. That doesn't mean though that the rest of us can't actually play the real. So I think there are some people out there that for whatever reason run into the same patterns in life that we all run into. And for some reason, they kind of have a natural inclination to put together patterns and reason using those patterns. And when they do, their brain grows because they just were like having to grapple with those patterns to use them to solve problems. And then now that their brain has more mental connections, they can build on that. And lo and behold, we have mathematicians inventing new math. Even as they were kids, not new math that the world had never seen, but new math for them. I think there are some people out there that have those natural inclinations. My rub is just because you didn't have that natural inclination to do it on your own, we could do it and we could help you intentionally. You could be like my coaches and help me learn to do a layup. We could intentionally help people to do real math. Unlike my experience, where people intentionally help me rote memorize and mimic. And then I had to be an adult before I realized, oh, that's not actually mathing at all. All right, so first thing we're going to do tonight. What does it mean to math the way mathy people math? I'd like to invite you to do a little math experience with me. I'm going to change my input really fast. Everybody see a blank screen up there? All right, so solve this problem any way you want, whatever relationships you've got. If you're kind of inclined to do what your 3rd or 4th grade teacher taught you and you're kind of going to like mimic it, maybe try to step out of it and go, if I didn't know that procedure, is there something else I could do? At least to get maybe an ish answer. Quote Joe Bowler there. Like if you just had to ish your answer, is there something you could do to kind of get like a feel for it? And then I would invite you to like actually try to solve it. So if I just gave you a problem like 15 times 18, everybody kind of think about that. What might be some relationships that you could use? This is super tricky in chat, but if you don't mind, if you have an idea of how to kind of give me a sense in the chat of how you might sort of split up the numbers or use a relationship that you own. If you've got something like that, maybe put a word or two in the chat that might give me an idea of Steph Curry. There's a good one. Yep, thanks. Kyle, I should have known you'd know Caitlin Clark. Nice. Ooh, and if you only practice layups, are you prepared to play the game? If you've never been in a game, you got to be in a game. Got to play. All right. People are thinking. Dr. J, that's a good one. Nice. All right, I'm gonna start with Sarah's. No, actually, let's think about. Nope, I don't want to do Ryan or Sarah's. Keep going, everybody. Those are good strategies. I'm gonna do one that I'm pretty sure a lot of people might be thinking and have dismissed, but we'll kind of go there. Did anybody kind of think about 15 times 18 as like a rectangle where you could say, I could think, and you didn't have to think about a rectangle, but maybe you thought about 15 by 18 or 15 times 18 as like 10 and 5? Anybody think about 10 times 18? Kyle's saying he might have. April's got 10 times 15 in there. I'm going to go ahead and do 10 times 18. Could I split up the problem? Instead of thinking about 15 18s, I'm going to find 10 18s, and then I would have to get the leftover 5 18s. Now, many people might be like, Pam, you don't know what 5 times 18 is. Yeah, but if I know what 10 times 18 is. So 10 times 18, everybody, is at 180. If that's 180, 5 is half of 10. What's half of 180? Bam, is that just 90? Cool. What's 90 to 180? Is that just 270? So that's one way that you could have done that. Now I am going to grab, golly, who was that? I think it was Sarah. I'm going to grab Sarah's strategy. So she's thinking about that same sort of relationship of 15 by 18. I'm going to try to make that look kind of similar. But she didn't think about 15 by 18. She said, I'm going to think about 15 by a little bit longer, 15 by 20. Because 15 by 20, I can do that's a pretty findable kind of thing. I could think about 15 times 2 and scale it times 10. I could think about 15 times 10 and double it. Whatever you do to get that. Is that 300? Does that track? I'm on live here, so there's every chance I might, okay, cool. Getting the good signal here. So if we've got 20 15s is 300, but I only want 18 15s, then I've got what, 2 too many 15s? So that's like 30 too many. All right, well, what's that total 300? Subtract that 30, is that also 270? All right, so 2 fine strategies to solve that problem. I know there were a couple of other strategies happening in the chat that I'm just going to ignore for a minute. Well, we might come back to them. In a problem string, the teacher facilitates the string by purposefully choosing strategies that get shared. It's a little different than a number talk when we choose maybe a million strategies, or at least several. In this case, I'm going to choose a couple because I want us to be really clear in the relationships that are happening. Everybody's like, I am solid now, Pam. 15 times 18, pretty darn clear that that's 270. Feeling it, feel those relationships. Bam, next problem. How about if I were to ask you something like 30 times 9? And if I could see everybody, I wonder how many people just like grinned a little bit. You were like, well, that one's not too hard. So 30 times 9, anybody, everybody? Think about 3 times 9 is 27. So then times 10, is that 270? Then I'm going to look as a teacher. I'm going to like scan the class and I'm going to go, and I'm going to just sort of see if anybody's like, and maybe I'll go, what'd you notice? And so did anybody, and I know there were a couple people that had this strategy in the chat, but did anybody notice a pattern? Got 15 times 18, 30 times 9. You're like, well, the answers are the same. I'm like, oh, well, that was probably just a coincidence. Probably just completely coincidence that those answers are the same. But I might go ahead and draw that 30 by 9 in relation to the 15 by 18. So then I'm going to be really clear to ask students, what would the 30 by 9 look like if the 15 by 18 looked like that? And just kind of help me based on that. So if I've got 15, but now it's supposed to be 30, but it better be what, like twice as long? Like if that was 15 and that was 15, maybe it's a little bit too long. Anyway, it's something like, that's a little too long. Let me get that 15. And then it's only supposed to be by 9. If this one was by 18, Then it, 9, it's like half of that. Again, I'm going to try to pull this language out of kids. And then, all right, so it's only half of that one. So that's interesting. So it was kind of twice as long and then half as wide. I wonder if we did that, like we could sort of took this, cut it in half, and then it's almost like we kind of took that half and tucked it under here. It's almost like we kind of have this guy, and over here we had this, but then we kind of, it's down here now. And so we end up with that 30 by, hey, that 30 by 9 is related to that 15 by 18, but it's like cutting it in half and rearranging. We didn't lose any area. Makes sense that the products would be the same. Okay, probably completely coincidence that happened. I don't know, it's kind of random, but we're going to say that the area of that guy is also 270. Next problem. How about if the next one is something like 16 times 45? And I'm just going to ask you to kind of, do whatever are there some relationships you could use? So let everybody think for a minute. Everybody think. When you're ready, you could throw something in the chat. Oh, Annie, nice. It's a nice middle school strategy. Getting some 1.5 in there. That would be a strategy I would want to encourage in about 6th grade. End of 5th, 6th grade would be a good place to do that. Anybody thinking about 16 times 45? Duane. It's almost like Duane's paying attention.
That is one of the few times anybody has ever said that about me. Thank you, Pam. You just made my day.
Sweet. I love these guys. So people are they're thinking, got a couple strategies in the chat. I'm going to suggest, it's always hard when I can't like see. I'm going to wait another minute. If you don't want to type out a ton of your thinking, you could just throw the product that you got, or you could type out your thinking. People are typing and they're like, we're typing, Pam, stop talking. That could be true. Kyle, I'll come back to that in a sec. So hold that thought. We'll come back to that in a sec. So I'm thinking, got a couple strategies going on. A couple people have said that it's 720. At this point, I'm going to have students share strategies. We definitely have people trying this sort of, let's move some pieces of a rectangle around. Let me just suggest to you, when I've actually done this with real students, because you guys are kind of fake students, when I've done this with kids, they will, if this 15 times 18 up here was new to them, they'd never thought about finding 10 of something and 5 of something. Often kids down here will try to do that. They'll go, huh? So there was a purpose in me doing this, because if you've never sort of chunked numbers like this, if you're a high school teacher, you haven't really thought about multiplication for a while, you're like, really, is this webinar going to be any good? Hold on, promise it's getting good. Then you might say to yourself, well, if this is 16, sweet, I could do 10 and 5 and then one more, 45s. That seems pretty doable. So I might, if this is the first time I've done this strategy with kids, I might represent that strategy, but I also might say to kids, hey, what would this rectangle look like based on the kind of the other rectangles up there? So the 16 is going to be a little longer than the 15, and the 45 is going to be quite a bit longer. I don't know, like maybe out to there. And so 16 times 45, at this point, I might not even ask kids to share their strategies. I've given kids a couple of things to think about up here. I'm going to make sure kids are pretty solid in that problem. Not ask them to share strategies, and then I'm going to say, hey, here's your next problem. How about 8 times 90? So Kyle, in one way, Kyle had put in there kind of a funny, I'm going to come back to it in a second, but that's one way I would deal with it, is I'm not actually going to even have kids share strategies for that one. I'm going to deal with you, Kyle, but just not quite yet. So then I asked for 8 times 90. Got kids smiling. Kids are like, 8 times 90, that's not too bad. 8 times 90, is that just 700? Oh, and what? Like, what is she doing? Now, my goal is at this point for students to go, ooh, is there a connection? So kids that were cutting this into 10 and 5 and 1, or they were doing something over here like with 40 and 5, or some kind of other like chunking relationship, which are fine, not a problem. But I'm hoping at this point to have caused a little bit of intrigue for kids to go, well, could we do that again? And then I might say, well, what would those rectangles look like if I were to draw an 8 by 90? If I'm looking at this 16 by 45, what would an 8? Well, 8's going to be half of as long as that. And then, so it's a little different, right? I didn't take that 15 to double it to 30. Now it's 16 to half to 8. Okay, cool. But then it has to be by 90. Now I've run out of room. So it was probably bad, Pam. I probably should have started my rectangles a little bit smaller so that I have enough room to get that 90 all the way over there. So dot, dot, dot over there, dot, dot, dot. It's going to carry over there. But 8 times 90, you guys just said was 720. And then I'm going to stand back and say, what's the relationship between those rectangles? So a couple things that I'm doing super purposefully is to try to make those rectangles somewhat proportional so that kids now have some kind of a sense of being able to go, how are they related? And could we cut this one in half and then tuck that up here to create the one that I just kind of drew below? I'd need a little extra space. So better Pam would have drawn my first rectangles a little smaller. So they'd be fitting on here a little bit better. And then I might say, that really seems interesting that for that very first problem. So if we look up here at 15 by 18, it seems like we kind of doubled one side and halved the other, and the area stayed the same. And for this problem, we kind of halved that one, but we doubled that one, and the area stayed the same. Interesting. We almost kind of have a proof without words when we have those rectangles on there. Next problem. How about if I were to ask you something like, I don't know, am I going to do Kyle's? This might be a moment where I do Kyle's. So Kyle, what did you do? 32 times 22 and a half. So I might say, hey, Kyle, I saw some stuff on your paper that was a little, tell us about that. And Kyle will go, yeah, I saw that you doubled the first one. So I turned that 16 into 32, and you have the other one. So I turned that into 22.5. And I would go, okay, why'd you do that? And he goes, well, because I was just mimicking what you did up above. And I'll go, oh yeah, you know what we do here? We don't like mimic. We like think about stuff. So you tried something. Did it work out for you? Do you like where it took you? And he might go, actually, no. And they're like, okay. Here's something super interesting that I didn't know as a very successful fake mather. I thought that people who did real math, when they saw a problem, saw the best strategy. I thought that they would see a problem and they would go, for this one, I'm going to double half. For this one, I'm going to use 5 as half of 10. For this one, I'm going to do an over. Like they had, no. The more mathy people I interview, which is part of the work I do, I interview naturally mathy people and I go, how are you thinking about that one? And then I try to get my brain to do that. And then I write problem strings to help other people do that. When I interview those naturally mathy people, they're really clear. They don't know the right thing to do at first. They try stuff. They go, well, I think about that. No, how about this one? No, how about this one? Actually, that one was the best. And it's super playful. They don't feel bad about choosing one that didn't, and they're playing around with relationships and then happily going with the one that slides the best that day. Let me, I'll come back to, remind me in about 5 minutes to talk about a research study. All right, so we have a few problems going on. Totally cool that Kyle went down a path that was like, not going to do that one. Let's go back and head into a strategy that works a little bit nicer. I wonder if we could do this doubling and halving thing for a problem like, I don't know, 3.5 times 14. Which one do you want to double? Which one do you want to halve? Now, I wish the chat was a little bit more exciting over there. Anybody want to throw in there which of those numbers you want to double? Just answer that. Which one of those numbers do you think you might want to double? Could double either of them. Yeah, and maybe my best question is, which one do you not want to have? Which one, if you find the half of, you're like, ooh, that's not so nice. Thanks, everybody, for joining in. So you could say, let's double the 3.5. So double 3.5, is that 7? Well, then if we're going to double one side, we had to cut it and move that area around. So we got to half the other one. Half of 14 is 7. 7 times 7, is that 49? Do you think then the area of this guy would be 49? If I had a little more time, I might draw those rectangles. In fact, I would probably with students. There's your homework, everybody. Draw those 2 rectangles. See if they actually find where you would move that piece of a rectangle around to kind of prove that it sort of works. Could you do something similar with a problem like, I don't know, 24 times 1.25 or 1 in 25 hundredths? Yeah, nice, Annie. Good notice. Could we double and half that one? Ooh, maybe we might want to half and double this one. We could double and half, but then we might end up with a Kyle problem. So people are thinking. Duane's like, go for the gusto. Don't do it once. So what, Duane, you're suggesting that we have the 24 to 12 and then double 1.25 to what is that, 250?
Yep.
And then you're like, don't stop there. Keep going. Is that what? Have that to
exactly.
6 and double that to 5. So go ahead. Go ahead.
Mhm. No,
Yeah.
that was you reading my
Yep.
mind.
Bam. What is 6 times 5, Duane?
30.
So you think this might be 30 and this might have a product of 30. Sweet. So we can do a string of problems like this to get kids playing around with area, perimeter, products, chunking area, moving things around, conservation of space. If I don't lose any area, what happened? I've got the same sort of area going on, that which means I have an equivalent problem that might be easier to solve. Got equivalent products. Could we look for problems that are easier to solve than finding equivalent problems that are easier to solve? That's a fantastic strategy. Let's see, how do I say this and say what I mean? Let me just think. There are those out there that advocate kind of general problem solving strategies. I'm okay with that, but I'm going to invite you to consider that I don't think it's enough. I think we can't just say to a kid, create a problem that's easier to solve. We can say that all we want, but I think we have to actually develop certain mathematical relationships so that kids can create equivalent problems that are easier to solve. And I think we can do that in part knowing what those major relationships are, and then using problem strings like the string of problems I just did with you to actually help you like start thinking about the relationships. I think we have to get picky about the major mathematical relationships that mathematicians actually use. A minute ago, I suggested that I was going to bring up a research project, and I actually remember. So Ann Dowker did a research study where she asked professional mathematicians. So I think we could call ourselves mathematicians. We do math for a living, but they didn't teach. So this is a group of people who weren't teachers. They weren't teachers, but they did math for a living. And she said, I'm going to give you a bunch of problems to solve, and then I'm going to take note of your strategies, sort of peer over your shoulder, kind of ask you if I can't tell. And then she took note of how they solve those problems. What percent of the time did those mathematicians use one of our traditional step-by-step mimicking algorithms to solve a problem? I mean, they're mathematicians, so maybe 50% of the time, maybe 75% of the time, 4% of the time. Close, Kyle. 4% of the time. What in the world were those mathematicians doing the other 96% of the time? Not mimicking and rote memorizing and mimicking. They were using, I would suggest, major relationships. Sometimes teachers get a little caught, I think, in a number talk ambiguity, where we think, oh, we've done number talks, and we get kids doing a bunch of different things, and it kind of gives us the sense that there's this vast unknowable set of strategies, and whew, glad you guys did some of them, and now I'm going to teach like the right way, and you guys mimic that, because then that's the general solution, because a lot of what you guys just did might not work for all the problems, and so I'm going to give you like this algorithm that's a general solution. Do we in fact need those general solutions? Or if we identified what the major relationships are, might that be enough? I'm going to ask that question and suggest that that's actually been part of the work that I've been doing for the last 20 years is researching how do mathy people actually math? What relationships do they actually use? And then looking at our number system and saying, is that enough? Which ones are if we had this small set of strategies, could we solve any problem that's reasonable to solve without a calculator? And it sure seems like 96% of the time, mathematicians did. That's interesting. All right, so first thing we did today was math the way mathy people actually math. I wonder if you would have run into one of these last problems here, like 3.5 times 14 or 24 times a 3-digit decimal. I wonder if you or maybe your students might look at that before the problem string tonight, or maybe before, obviously several of you had learned that doubling and halving strategy before. But if you had never thought about doubling and halving before, and you saw really many of these sort of clunker problems, how many of them might you have gone, whoa, okay, I better But tonight, you were like, ooh, I bet I could cut that in half and slide it over there. I could double one of them. I could half one. Let me play with which one I'm going to double, which one I'm going to half. That playful idea of, ooh, which relationship can I use right now? That is mathematical behavior. Let me give you one more bit of that. In that same study, Ann Dowker went back to some of those mathematicians on a different day and said, hey, I'm going to give you just a different set of problems. If you wouldn't mind just solving them again. I'm not actually sure she lied, but on the second day, she gave them the same problems. What's fascinating to me is that many times on that second day, mathematicians used a different strategy. That plays out with it's sort of what their mind was busy with. They were thinking about a certain relationship, maybe doubling and halving had something to do with the work they were doing that day. And so they took that strategy. But on a different day, maybe some other relationships were happening. And so they took a different sort of path. I think our goal for our students is to develop the major relationships that lead to the major strategies. And then kids have choice. Sometimes a lot of my colleagues talk about agency in mathematics. I don't think we can have more agency than having a ton of choices. Not too many, just the major relationships. When I have the major relationships and I've built them, now I really have agency to choose what I'm doing. I think we can cut down on that. When are we ever going to use this argument? If we can make things playful and intriguing and kids have agency to choose how they're going to go about solving problems. All right, first thing we did today, math the way mathy people actually math. I'm going to invite everybody in the chat, throw 1 or 2 words. What are you thinking about this experience of mathing the way mathy people actually math? Maybe 1 or you can do 2, 1 or 2 words. What are you thinking about right now? Yeah, Duane, same here. And I would have tried to have done it in the air so I looked cool. Done the steps of the algorithm. Now I look really cool. Or not. Well, Duane, I'm glad that I've perked this idea of major relationships. I think it's a super important one. I think it's really, really, really important. Yeah. Efficiency, purposeful, flexibility. Nice. Be kind of nice to be flexible. I'm liking it. All right. Thanks, everybody. Appreciate that. Second thing to do tonight. I'd like to teach you. Oops, that's not the one I wanted to open. I'd like to teach you to see the shark. What in the world am I talking about? So may I invite you to consider that I think for the thousands of teachers that I've worked with over the years, I think often when they were students, that they had a distorted view of the nature of math. I'd like to introduce a metaphor to you that might help us kind of carry this conversation forward. Does anybody remember these? So this was called a magic eye. If you were alive in the 90s, maybe you remember it was kind of a big deal. They're still around. You'll see them every once in a while. Everybody's like focused on their computer screen. Maybe I'll stop talking for a second. If you focus behind this image, so you kind of almost let your eyes relax a little bit so that your focal point is behind the image, you kind of almost look through it. Many people can make work that a 3D image pops out. So I'll give you just a second to try that. Okay, a couple people are seeing it. Okay. What's really important here is not whether you can see the 3D image. What's really important is that you've had the experience of trying to see the 3D image. You're like, I don't even know what I'm supposed to do. What do you mean focus behind the image? What do you mean relax my eyes? You're like giving it a go. If I tell you right now, if you can figure out how to see a magic eye, you should see a 3D shark. This is a shark. All right. I invite you right now to take this metaphor. Seeing this shark is kind of like, where do we usually lose kids? Subtraction with all the crossy outies and little ones and zeros. Or how about long division with all those steps? Or how about fraction anything where we mix up all the rules? How about pick cross multiply and divide? Pick a place in mathematics, algebra, solving equations, where we often lose kids. Pretend or go with me on this metaphor that it's kind of like looking at this magic eye. it's almost like we have kids in the room that go, oh, cool, it's a shark. They're like, I see the shark. They, for whatever reason, they have a natural proclivity, a natural inclination to put together to be able to see this image. Or in math, they put together mathematical patterns and they were able to like see the math behind it. And they go, check it out, it's a shark. Be the teacher in that room. Well, let me do the teacher just a second. So I think that's one way of kind of like kids can see the shark. I think there's a whole group of kids that never see the shark, in part because the teacher says, hey, see this? And the teacher says, this is a shark. And the kids go, what? And the teacher goes, yeah, see these squiggles? Does everybody see some kind of vertical squiggles? And then there's like this wavy thing. Can you kind of see the squiggles and the wavy thing? So if you see those squiggles in the wavy thing, the teacher says, this is a shark. And the kid goes, I don't see a shark. So I'm just going to memorize that when I see this, I've got to like, there's these squiggles. I've got a squiggle. Okay. This is so lame. This isn't anything to do with my life, but I'll memorize your squiggles. Okay. Math class is so lame. When am I ever going to use this? Squiggles. Got it. They squiggle that day. They circle all the squiggles and they circle their answer at the end. They get credit for it. They move on. Math class moves on. I suggest to you that many of our students never see the actual shark and they just memorize squiggles and they get credit for it. That's the crummy part, is that mimicking of credit of squiggles they get credit for. Like, ready? That's what I did. I was the penultimate squiggler. Like, I could squiggle with the best of them. I just memorized all the rules, spit them back out, got credit, and thought I was doing real math. Imagine my midlife crisis when I realized, as a high school math teacher, that I was actually doing fake math and I wasn't really real mathing at all. But also imagine my joy and wonder when I realized I could, that it was possible for me to see the shark. I think there's a third group of students that says, there's a shark? Cool, I want to see the shark. And the teacher goes, yeah, see these squiggles and the little, and they're like, no, stop with the squiggles. I want to see the shark. Like, I believe you, there's a shark there. And the teacher's like, no, like, pick up your pencil and start doing the squiggles. And the kid's like, I don't know what you're, like, why are you holding me back? Like, I want to see the shark. This is stupid. Math is dumb. I want to see the shark. Why are you holding out on me? Have you ever had a kid where you're like, okay, like, start writing down your homework and, start doing the problem. And the kid's like, no, I don't get it. And you're like, look, I've explained it 3 times. Like, you got to pick up your pencil, start. And they're like, no, I want to see the shark. Here's the real interesting part, I think. I mentioned that it was distortions. You guys are still trying to see the shark. I love it. Be one of those kids who then becomes a teacher. Be the kid who saw the shark. I bet I have several people on tonight that are almost looking down on me a little bit because you're like, Pam, math is just, you just see it. Would you consider that there's a possibility if you naturally saw the shark, that you ran into relationships and connections and you were like, oh, I could use that. One of the ones that my kid did was, you don't have to know your 5s if you know your 10s. You can just multiply times 10 and kind of have to get 5. Another one, I was in a 9th grade classroom and a guy raised his hands and he goes, how come you can double one and half the other one and it works? And I smiled and I was like, well, it's a good thing I'd heard of that before now, because 2 years ago I wouldn't have known what you're talking about. And I was like, double what and half what? And he talked about the strategy that we did today. He had just noticed that you could do that on his own. He could see the shark and he kind of wanted to figure out how the shark worked. Be that kid and become a teacher. You're excited. You like the shark. This has been fun for you because it was naturally good. You go into your class and you're like, all right, everybody ready? Here's a shark. And like, there's a couple kids that can, and the rest of it, and you're like, oh, this is why my teacher did that squiggle crap. Okay. All right. I don't know why you guys can't see the shark, but here, squiggle. And then they teach their kid. They don't know why they can't. They don't have any experience to draw back on because they did it on their own. And so without any experience of what it looks like to teach kids who don't naturally see the squiggle or naturally see the shark, then they sort of force the squiggle. Be kids like me who saw math as a disconnected set of facts to memorize and rules and procedures to mimic. I become a teacher. I show kids the shark and I go, hey, everybody, this is a shark. Ready? Squiggle, 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 squiggle. I got a kid in my class. I'm just going to look at Kyle because you're on my screen, Kyle. I'm going to say, Kyle, I do it. And Kyle goes, there's a shark. And I go, no, Kyle, you got to show your work. And Kyle's like, it's a shark. And I'm like, yeah, but you got to show me the squiggles. And he goes, It's a shark. This is so, I just know it. He has no idea how to like show his thinking or whatever. He's like, it's obviously a shark, ding dong. If I'm the teacher who's never seen the shark and I believed that math was squiggling, I'm a little bit, it's the only way I can teach at this point. I don't know how to see. I've never seen the shark. I think, especially leaders of mathematics, that if we could recognize the possibility that we are working with teachers and kids, some who can see the shark and others who can see the shark, but we need to know how to help them actually see the shark, that we need to get out of, well, you can't see it right away, let's just squiggle. You can't get that layup right away, you go over here and play that fake game of math. I don't want to play the fake game. I want to play the real game of math. I want to do tasks like we just did, where I'm building relationships and connections, and I can continue to see the actual shark, play the real game of math. All right, so the first thing we did was math the way mathy people math. Then I taught you how to see the shark, or at least the distortion. Before I move on, I'll just show you this quick little video for those of you that are a little mad at me right now because you didn't actually see the shark. Here's a way of sort of shifting the pixels. So you can, it's not what it looks like totally because it's not 3D, but it does give you an idea of kind of how they create autostereograms. It's about, they create the pattern and then they shift. And that shift is what has your eyes do that focus thing behind. So anyway, a little bit about, it's kind of fun. I now know more about autostereograms than ever before. All right, so the third thing that I invite you to do tonight, how can we avoid the traps of algorithms? First question I want to ask you in this third section, avoiding the trap of algorithms, is what is the purpose of math class? And Annie, I'm having a hard time keeping the chat going. I'll look at your question, I promise, in just a minute. What is the purpose of math class? Would you consider that I think many people who've never seen the shark, who squiggle, that they say to themselves, think about your math class experience when you were a student. I think many teachers say, all right, what is the kind of problem kids need to solve today? Okay, it's that kind. Let's see. What is the fastest, most efficient, most foolproof way that I can just show everybody they can all do it? Really, they don't have to learn anything new. It just calls on things they've already sort of memorized and they've already been mimicking, and I can just kind of put them together in a new way, and they'll all get answers. They can take it home. Their parents will recognize it as something they've seen before. Everybody's cool. Bam, that's the way that I'm going to teach kids. If the purpose of math class is for kids to get answers, that's reasonable. We can squiggle and get answers, and it might be easier than actually teaching kids to see the shark. If that's not the purpose of math class, then what is? I invite you to consider that the purpose of math class is to develop mathematical reasoning. Now, caution, here I don't mean some fuzzy think better. I actually mean reasoning mathematically. You're using real mathematical relationships. Your brain has mathematical connections that you're using. So I know this is a little bit of a busy graphic, but just quickly, what that means is that we want kids to learn to count, and we build on that to think additively, and we build on that to think multiplicatively and proportionally and functionally. If I look at this outer oval, this is sort of the high school level where I want kids to solve problems about functions and relations and graphs and tables and transformations. And that is built on and based on proportional reasoning, which is the land of the middle school. And that's built on and based on multiplicative reasoning, which is the land of the third, fourth, fifth, sixth, seventh grade teacher. Notice I had overlap there. It overlaps into middle school. Additive thinking is the land of the first, second, third, fourth, fifth grade teacher. Again, overlap. There's grade levels that teach both of these, and that's built on and based on counting strategies. Now, you might say to me, Pam, this is just our set of standards. First, kids count, then they add and subtract, then they multiply and divide, then they solve proportions, then they do that stuff no one understands. But I'm actually not suggesting that they're just getting answers to addition and subtraction questions and getting answers to multiplication and division questions and solving proportions, getting an answer. I actually mean that they are literally building new mental strategies, and that they are building a new way of thinking, and that their brain is reasoning more sophisticatedly. That's noteworthy. That means it's not going to be the most clear, most instantly successful, most foolproof way for kids to squiggle. It does mean I'm actually going to build neural mathematical connections in kids' heads so that they think and reason more sophisticatedly. So here's a rub. What if, but Pam, when we squiggle, kids get it. They get the answer, they circle it, we move on. It's fantastic. Until, of course, the next thing, and then they mix up the rules, or the next grade, and then their brains aren't thinking. Let me prove to you one, or invite you to consider one trap of algorithms. We solved today the problem 16 times. Whoops, come back. Oh, come on, Pamela. Sorry. Go back, go back, go back, go back. Touchy iPad today. We solved the problem 16 times 45. I'm going to put that in the multiplicative reasoning section there because we should be building multiplicative reasoning if we're having kids solve that problem. Do the standard algorithm with me. Notice that the standard algorithm or traditional algorithm has us solve 6 times 5 first. So if I'm a kid doing the algorithm, first of all, let me point out that it's asking me to solve, to use the least consequential numbers of the problem. I'm not thinking about 45 16s or 16 45s. I'm thinking about 5 times 6. Like the smallest parts of the numbers is where I sort of focus first. That's interesting and also works against our intuition. But then be the kid that says, all right, I'll do it. Fine, I'll do your thing. I'm supposed to do this 6 times 5, 6 5s. 5 plus 5 is 10 plus 5. And I skip count to get those 6 5s. And I get that correct. And I put this up here. And then I go, now I need 6 4s. 4 plus 4 is 8 plus, and I skip count to get those. And I get that correct. And then I have the magic 0 and then all these. And then I do all of the steps of the addition algorithm. And I get the answer correct. And my teacher says, yay, you're a multiplicative reasoner. What kind of reasoning was it when they were doing those single digit multiplication facts as they were skip counting? What kind of reasoning is adding all of those factors together? Is that multiplicative reasoning? Y'all, that's additive thinking. I should be building multiplicative reasoning, but I'm getting away with additive thinking. And I think that is the biggest trap of the algorithms, is that I can squiggle with stuff I've learned before and never build my brain to reason in a more sophisticated way. That's noteworthy. Let me give you one more quick example. What if I were to solve a problem like a proportion? Often teachers will say, oh yeah, I know how to do that. You cross multiply and divide. I heard the other day, bat and ball. Okay, don't pick that up. Y'all, if you make something super cute in math, chances are really high you're in fake math land. You're like, how do we memorize these squiggles? Okay, let's come up with a story around it. And if math is about memorizing squiggles, then sure, come up with a story. If math is about actually seeing the shark, stop with the cute and actually teach stuff. But here's my point with this algorithm. If I teach kids to cross multiply and divide, I'm supposed to be building proportional reasoning. Multiply and divide, if I do that multiplication with the traditional algorithm, I could be using additive thinking. So one of the largest traps of the algorithm, I call the less sophisticated reasoning trap. That I can look like I've built a certain kind of reasoning, but I'm actually using reasoning in the level or levels before. And my brain then doesn't get a chance to actually build that kind of reasoning, and we get what we've gotten. Now we're just going to try to memorize some more. There are 2 more traps that if anybody who joins us at CMC Central, when I'll be there in a couple weeks to speak, I'll talk about 2 more traps for algorithms. I'll let you see them really quickly here. There's a digit-oriented trap. I mentioned it a little bit, but we'll get into it more. And then the definition of math, which then leads to what our identity is all about, trap. But I'm not going to take the time to do that. How can we actually avoid some of the traps? Let me give you 2. I'm going to give you 2 quick things to think about to avoid the trap of algorithms. 1, use problem strings. Problem strings are amazing ways to get kids, give them a high dose of patterns. A problem string is a purposeful sequence of problems that high doses kids with those same patterns that mathy people ran into. They only had to run, some people only have to dribble a couple times and they're doing a layup. I needed like 3 years of layup school. Many of us need more experiences. Problem strings high dose kids with the patterns for major relationships. Another thing that we can do is build foundations for strategies by, I call these smudge problems, where we give kids relationships and we say, hey, if you know it's 1 to, what is that, 6? If you know it's 1 to 6, and then oops, I dropped ice cream on my homework. Oh, crumb. What should be there? I got to fill in that slot right there. Well, if this is 60, then that would have to be, what is that, 10? Okay, if that's 10, I know 10 of them now. I get 60 of them now. Ideally, I would have done this first in context. But if it's 1 to 6, and well, come on, Pam, 1 to 6 and 10 to 60, then how do I get 9? If I only need 9 groups, oh, just get rid of one of those groups. What about 11? Oh, just add a group. And if I can do that using the major models, ratio tables and open arrays and open number lines, if I can use that in those major models, now it doesn't kind of matter how kids are solving problems. They can be using a calculator to get the answer. I'm sort of forcing the thinking happening here because they're kind of filling in someone else's strategy. We can do that with open number lines, with addition, subtraction. We can do that with bigger numbers on open arrays. We can do that at middle school with similar figures. Some examples of smudge problems where I leave the spot open and I say, hey, how was Andy finding that missing figure? If I know these relationships, what was Andy doing? What was Anne? Hey, I got Annie on tonight. What was Anne doing? And then what was Allison doing? And I'm going to fill in the blanks on that's a way. If you've got kids who are used to rote memorizing and mimicking, I can say, okay, do what you did to get an answer. Hey, but in this class, we're about building reasoning. So I don't really care about your answer. What I care about is how you got there. That's not to say we don't care about answers. That's to say that if we do this work, the right answers take care of themselves. All right, y'all, there's some ways we can think about. If you're interested to know, Duane said earlier, I haven't thought about the fact there are major strategies. I'm announcing to the world, I think there are major strategies, and here's what they think they are. Here's an ebook that you are welcome to download tonight. I'm going to give you a link in just a second. It gives you some sample problem strings to try in your classroom. You can use that link. You can grab that QR code. Cole's typing it in. He's going to put it in the chat. Did I just read your mind, Cole? Man, it's scary how I could read that guy's mind. So y'all are welcome to grab that. I'm going to grab some questions just a second. But before I do, just quickly, if you're interested to know more about Math is Figure Outable and what my small team and I are accomplishing, you can check out the Math is Figure Outable site. Did you get it? Yeah, you did. Thanks. You can check out the Math is Figure Outable podcast where Kim, my co-host, and I do short episodes where we math the way mathy people math and talk about how we could teach that way. I'd love it if you join me on Math Strat Chat. Kyle's a frequent. I think I can see Duane. I don't know if I see Cole there. Do I see Cole? Maybe. There you are. All right, Cole, sorry. Pick your social media. I'm almost on all of them where you just can Google Math Strat Chat. I throw out a problem to the world and people from around the world throw in their solutions and chat about each other's strategies. You can check out my brand new book from Corwin called Developing Mathematical Reasoning, Avoiding the Trap of Algorithms. That link right there will get you the pre-order. I don't know that you're going to be able to type that one in, Cole. That was kind of long and ugly. Sorry. Maybe I'll let it sit there for just a second. I'm going to take questions just a second, but before I do, I'll leave that on there while I leave you with this. I mentioned earlier that I played internationally. When I played basketball in Switzerland, it was a riot. The international rules at that point said that when the ball went out, you just grabbed it, threw it in, and the game went on, kind of like soccer. It was super fast paced, always multiple different languages. There were so many not cohesive, incoherent, conflicting voices. You kind of just learned to ignore everything and watch the ball. Y'all, our team did something that I'd never done before in practices. Our coach had us partner up and run drills together. We would cheer each other on and encourage each other. We were in it together. My partner's name was Flavia, spoke Italian. She would yell at me as we were running. I was sucking air. She would yell, "Die, Pamela, die!" That means in Italian, "Go, Pam, go." Y'all, I've never had somebody yell at me to die. It was so hard not to laugh or cry when someone's yelling that at you as you're sort of at the end of your endurance and trying to push yourself. But it was so helpful to have that teammate in your corner, encouraging. We were better together. As you leave and think about your teaching, I invite you to join the Math is Figure Outable movement, where we kind of have a coherent message, where it's not about different competing voices. It almost might seem like different languages. It can be hard to know where to pay attention and what to watch. I invite you to join the cohesive, coherent Math is Figure Outable movement.
Just a big, huge thank you, Pam. That was wonderful. And we are so excited to have you joining us at the upcoming CMC Central Symposium. So those of you that are not registered yet, there is still time to register. And Pam will be live up on stage Saturday morning, bright and early. So please make sure to join us at the Central Symposium, as well as continue to join us and spread the word about our Inspiring Math Minds webinar series. So we will be back here the third Thursday in March at 4 o'clock with another wonderful speaker. And so please make sure you're spreading this far and wide to all your colleagues. And if you happen to miss today, all the recordings are archived on the CMC website. So you can come join that. And we won't. Pam may have to join us on this one eventually. But if you didn't get enough of Duane and I today, you can also join Duane and I on the Math on the Rocks podcast, where we are talking about all the rocky topics in California mathematics right now. And boy, are there a lot of them. And just a big thank you all for giving up an hour from 4 to 5 o'clock after you've taught all day, and you decided to come join us. So just thank you for being here, and we will see you next month.